Hi, everybody. This is Miss McClellan here to go over notes 4.2.3 with you. Okay, so the question is, how can I determine the angle measure? If we're given the lengths of two sides of a right triangle, can we work backwards to determine the measurement of the unknown angles? And we have a learning goal, which is that we can do just that. I will be able to determine an angle measure when given the sides of a right triangle. At the end of the lesson, we'll go and do a little bit of an update to one of our previous notes, where we will add this last little piece to it. We'll be updating our triangle graphic organizer, which was from notes 4.2.1. Okay, here we go. First problem, 4-78. Mr. Gao needs to build a wheelchair access ramp for the school's auditorium. The ramp has to rise a total of 3 feet to get from the ground to the entrance of the building. In order to follow the state building code, the angle formed by the ramp and the ground cannot exceed 4.76 degrees. So we've got a couple pieces of information so far. Needs to rise 3 feet. Okay. Mr. Gao has plans from the planning department that call for the ramp to start 25 feet away from the building. Will this ramp meet the state building code? Okay, well, anytime I have a problem that involves a story in geometry, I like to draw a picture of it so that I can organize my mind. Some of us have pictures in our minds and some of us don't, but we can all make drawings. Okay, so here's an angle. And we want this angle to be at most 4.76 degrees, but we don't know if it does that yet. Okay, so it's going to start. This is the building. And my ramp needs to rise 3 feet. And my plans are to have it start 25 feet away from the building. So this distance here would be 25 feet. And this distance here would be 3 feet. So Mr. Gao needs to know if the angle will be 4.76 degrees or less. It would help nobody if the angle is more than 4.67 degrees. Sorry, 4.76 degrees, because then it would be too steep and it would be hard to roll up it. Okay, so part B, select the correct trig relationship. What do we need? Well, we're dealing with the opposite and adjacent sides of a triangle. So that means we're going to be using tangent. Tan of an angle is equal to the opposite side length divided by the adjacent side length. You know that because the tangent is defined as the ratio of opposite over adjacent. Okay, part C. We're going to use this trig table to find out if this is going to work. So we know that we're using tangent. And we want to know if tangent is going to work out that way. So let's see. I've got tan of my angle is about equal to 3 over 25. I put 3 over 25 in my calculator. Here I go, getting my calculator. Do. 3 divided by, you see that? 25 equals 0.12. So I need my angle, my tan of my angle to be about 0.12. This is how we used to do it before we had calculators for everything. I would have done 3 divided by 25 by hand. I would have gotten 0.12. I would have found that on my list of tangent things. The closest possible value is right here, 0.1228. And that would be for an angle of about 7 degrees. All right. So that's kind of a problem because we wanted the angle to be 4.76 degrees or less. So let's see. Let's read part D and see if we're going to make any conclusions here. If Mr. Gal builds the ramp exactly to code, how long does the ramp need to be? So 7 degrees is not good, no good. We need to figure out how long the ramp needs to be. I know it has to rise 3 feet because the door is 3 feet off the ground. So that's not negotiable. I need to have a right angle because buildings are in general built perpendicular to the ground. And I want to know how long the ramp is going to need to be. So let's see, this will be X, this would be my angle. Now, if the angle was less than or equal to 4.76, then just using the trig table and realizing that this is sine, so I have sine of my angle equals 3 over X but I'm not really going to be able to do X. Yeah, I can do X. Sure, I can. Okay, so I'm gonna just put in 4.76. That's gonna give me the limit of my length. Sine of 4.76 equals 3 over X. I cross multiply, and that gets me, I'm gonna write it over here, X times sine of 4.76 equals 3. I divide both sides by sine of 4.76. And I get X equals whatever that is. So let's put it in our calculators. Okay. Sine of 4.76 is that number. And I need to do 3 divided by that number. So 3 divided by sine of 4.76 degrees is about 36 feet. So the ramp needs to be about 36 feet long. Really, I should say 36 point, about 2. It was 36.15 and I don't think we can measure feet to much more exactness than a tenth. Anyway, I know because I set the angle to 4.76 to code and solved for X. My ramp needs to be that long. So if I were to go out and get a very long, very long piece of wood, something that is 36 feet long about, I could have that connect to where the doorway starts, and it wouldn't be too steep. It would meet code. It would be fine. Longer would even be better, but this would be good enough. That's an example of something that our functions would absolutely be used for. Our functions are so fundamental. They're used in everyday life. Next problem, 4-79. We consider the triangle below. We need to determine the measure of angle A. Now, we know that we'll be dealing with cosine because we have opposite of A. It's over here. This is adjacent, and this is hypotenuse. And I promise this is the last problem for which we will use guess and check. After this, we are going to calculate these more directly with our calculators. But for now, we still live in the world of guess and check. So cosine of A is equal to 14 over 15. And I'm going to use guess and check. That's almost 1. Let's see. First, let's do 14 divided by 15. Like 0.93. And then I'm going to start guessing angles. Cosine of 10. 0.98. Cosine of 20. 0.93. Cosine of 30. 0.86. What are we trying to get to again? Was 14 divided by 15? 0.93 repeating. Okay. Cosine of 30. That was too big. No, that's too small. Cosine of 20. That's pretty close, but it's still just a little bit too big. It's 0.939, and I want 0.933333. Let's try a little bigger. Cosine of 25. 0.906. That's too big. Let's go between them. Cosine of 22.5. That's a little bit too small. Okay. Cosine of 21. 9335. What about 21.2? 0.1. 333. 0.05. Ooh, that's really good. What about 0.06? Ooh. 5, 1, 2, 5. Okay, we actually don't need this level of precision. I'm just having fun now. It's about 21.05 degrees. Not percent, degrees. Okay, now we'll determine the measure of B. There's a couple of ways I can do this, but I'm thinking the fastest way will be triangle sum theorem. So I know that the angle of A is about 21, which is 90. So this has to be 180 minus 90 minus 21, which is I'm going to do it on the calculator. 90 minus 21. $70. No, 69. Angle B is about equal to 69 degrees. Okay. And C, what knowledge about angles and triangles could help us solve for angle A given angle B? The triangle sum theorem, which we used. I could have done this using sine or cosine, but I didn't want to because guess and check annoys me. Okay, next problem is 4-80, but we are going to hold off on it because I want to tell you and show you how to do this on a calculator, because your calculator can do everything that we were just doing. And it is based on the concept of an inverse. So just like subtraction undoes addition and multiplication undoes division, we have inverse trig functions. The inverse trig functions undo the trig functions tan, sine, and cosine. So in particular, specifically, inverse trig functions are used to solve for measures of an angle of a right triangle when the ratio of two sides is known. The opposite or inverse, it's the opposite or it's the inverse of determining a ratio from a known angle. So for example, I know that sine, I know that tan of 45 equals 1. The inverse, this tan of 45 takes me to 1. The inverse of this would take me back to 45. The inverse trig functions that are used in this course are inverse sine, inverse cosine, and inverse tan. And they're written as, I'm not sure you can see it with the recording, so I'm just going to rewrite them. Sine with a little -1 written in what would be a exponent, but it's not an exponent, just a little -1, cosine -1, or tan of -1. And this is pronounced inverse sine, inverse cosine, and inverse, we usually say tan, even though it's really tangent. So when you see tan with little -1, that is read as inverse tan. And similarly for inverse sine and inverse cosine. Yeah, so where tan of 45 took you to the number of 1, inverse tan of 1 would take you to 45. It just does, it goes backwards. Okay, so right here we have an example that shows how the inverse cosine can be used to calculate a missing angle, theta. Here we have a triangle, and again, I'm not sure if you can see this on the recording because I know that the production value is not like super high. So I've got a triangle with an adjacent leg, length 10. It's a right triangle. The hypotenuse is length 13. And I'm just going to rewrite everything, even though it's on your page. Cosine of the angle is equal to 10 over 13 because that's opposite over, that's adjacent over hypotenuse. And the angle itself can be found by writing cosine with a little -1, read as inverse cosine of that ratio, 10 over 13. And your calculator can do it. So we use our calculator. We evaluate inverse cosine of 10 over 13. If you have a TI-84, which is what we have in our classroom, you can use that. But I mean, any scientific calculator will have a way to do this. It's usually either the second button or the inverse button that you press. I'm going to press the second button because that's what I have on this calculator. So, second. And I want inverse cosine, so I press the cosine button, but I've activated the blue command above it. Inverse cosine of 10 over 13 is 39.7151, which is about 39.7. So I get theta is about equal to 39.7. Check. Okay, then we have a little bit of practice. Straight practice calculating cosine. The cosine of the angle is 2 over 5. Therefore, the angle must be, well, I'm going to use inverse cosine, and I should zoom in a bunch for you. Hope you can see this. Okay, cosine of the angle is 2/5. Let me turn down this brightness. So the inverse cosine, I press second, I press cosine of that ratio is 66.4. So the angle is about 66.4 degrees. Next, I'm given that sine of an angle is 4 over 8, meaning that if I had this triangle, and here is the angle, and this was 4, and this was 8, then sine of that angle would be equal to 4 over 8. What's the angle? Well, I'll go backwards. I'm given the ratio, so I'm going to plug that into inverse sine. Sine of 4 over 8. If you wrote 1/2, great. If you wrote 0.5, great. If you wrote 4 over 8, it's all the same thing. That angle is 30 degrees. Next, tan of 3/5. Okay. I activate inverse tan, and I put in that ratio 3 over 5. I get 30.9. The angle is about 30.9 degrees. I'm rounding all of these to the nearest tenth, except for the case of sine 1/2, because sine of 1/2 is exactly 30 degrees. All right, next. Now I've got to do that. The problems are not done for me. So I'm going to set these up before I go back to the calculator. Okay, number 4. This is opposite my angle. This is adjacent. So I'll be using tangent. I like to use SOHCAHTOA when I start needing to keep track of these. This is tangent because I have opposite and adjacent. So I'm going to say tan of my angle is equal to 14 over 29. And then to go backwards to get the angle from that ratio, I'll say inverse tan of that ratio, 14 over 29, is going to give me my angle. And I'll put that in a calculator in just a moment. All right. Next. Okay, I'm still going to be using SOHCAHTOA. I have my angle, opposite my angle is 10, and I have my hypotenuse. So since I'm using opposite and hypotenuse, I'll be using sine. So I have sine of that question mark is equal to 10 over 39. I need to go backwards to get the angle, so I'm going to use inverse sine. Inverse sine of 10 over 39 will equal my angle, and my angle will be whatever that ends up being. Okay. I have opposite my angle is 12. I'm given my hypotenuse. I have opposite and hypotenuse, so I'll be using sine. So I have sine of my angle is equal to 12 over 24. I already know this is going to be 30 degrees, but I'll do it anyway. The inverse of 12 over 24 is equal to my angle. And so my angle must be whatever that spits out when I put it in my calculator. Next. Okay, and given my angle, I go across to find the opposite. I don't need the opposite because it's not labeled, but that's how I figured things out. My hypotenuse is 8, and my adjacent side is 6. I know I'll be using cosine because I have my adjacent and hypotenuse. So cosine of my angle is equal to 6 over 8, adjacent over hypotenuse, which tells me that I need to find my angle. So the inverse cosine of 6 over 8 is equal to my angle, and my angle must be whatever I get when I plug that in, which I'll do last. Speaking of last problem. Ooh, I have choices. Okay, it shouldn't matter how I do this. I'll use sine. I like sine. Okay. Sine of my angle is equal to 14 over 50. So the inverse sine of 14 over 50 is going to equal my angle. So my angle must be whatever I get when I plug that in my calculator. Now I'm going to go ahead and plug all of these in my calculator. Okay, first one is about 25.8 degrees. Next one, I'm plugging inverse sine of 10 over 39, and I get about 14.9 degrees. If you were to write 15, well, no. Let's do it to the nearest 10th to be consistent. Okay. Next one. This one is inverse sine of 12 over 24. It's exactly 30 degrees. I knew that because it's the same as the previous problem. The ratios are equivalent. 4 over 8, 12 over 24, same. Okay, next, cosine of 6 over 8. I'll be using, inverse cosine of 6 over 8. Is it's telling me that it's 1 because I'm not pressing inverse cosine. I knew I was wrong. Okay. So if you were to put this in as cosine, I'm going to show you my error. If you do cosine of 6 divided by 8, that's a pretty small number. I know that cosine of 0 is 1, and cosine of 6 over 8 should be almost the same thing. But this is not the right answer because I'm not trying to find the cosine. I'm trying to find the inverse cosine. This is like saying an angle of 6 divided by 8, which is like an angle of 0.75 degrees. It's small. 0.75, not 75, 0.75. But that's not what I'm trying to do. I'm trying to find an angle from a ratio. In order to do that, I need to use inverse cosine. So inverse cosine of 6 divided by 8. Aha. See, it's different. 41.4 degrees. Approximately. Next. Okay. Inverse sine of 14 over 50. It's about 16.3 degrees. Okay, that's the end of this page. We've got one more page to go, and then we're done with the notes. Last page. Here we go. Okay. So now that we have our method defined for us and we no longer have to use guess and check, let's do a couple of practice problems, just 3. And this is really focusing on strategy because we've already done the problems that we're used to. All right, so examine the triangles below. I mean, we've already done the method, but let's see about thinking and doing the method all at once. First of all, notice that it gives us a warning that the diagrams are not drawn to scale. That's like always true in this class. Well, you can assume it to be true that the diagrams are not drawn to scale, but the fact that they're taking the time to say so means it's going to come up. Look through all the triangles first and see if they look familiar. If possible, determine the angle measure or side length without using a trig tool. I'm going to read them through all the way. Okay. For all the other triangles, identify which tool to use based on where the reference angle, theta, is located and which side lengths are involved. Write and solve an equation to determine the missing side length or angle. Okay, so for part A, I have this triangle. The angle is in the upper corner. This is opposite, this is adjacent, and this is hypotenuse. Now, I have cosine of the angle is equal to 12 over 24. Which means sine of 90 minus the angle is equal to 12 over 24. So I've got options about how I'm going to solve this one, either directly or indirectly. I'll do both. But first, let's look at the other triangles. This one. This one doesn't look like an isosceles triangle, but I'm given that both of the legs are length 8. So it is isosceles. I'll draw it again because I don't like the way it looks. But we were warned, the triangles are not drawn to scale. 8, 8, angle, angle. The angles have to be the same and they have to add to 90. Theta is 45 degrees. Okay, next one. This, I don't know anything fancy about the angle 57 degrees. This just has to be solved directly. Got my opposite sides, I've got my hypotenuse, and I'm going to write sine of 57 degrees is equal to 7 over x. That said, I'm not being asked to find the angle, so I'm not going to use inverse sine. I'm going to multiply both sides by, well, I'm going to cross multiply, so I have x times sine of 57 equals 7. Divide both sides by sine of 57. And I get x is equal to 7 over sine of 57. And if I throw that in my calculator, let's see what I get. 7 divided by sine of 57. That's about 8.34, about 8.35. You could do 8.34 if you want. All right, back to part A. This was the most interesting of them to me, so I saved it for last because it's my favorite. Okay, first of all, I could do cosine of the angle equals 12 over 24 immediately, just using inverse cosine. So let me do that. That means cosine inverse of 12 over 24 will equal my angle. But I could also do this. I get my angle at 60 degrees, by the way. I could also do this way. Now, from my previous problem, I had 2 examples where I found out that the sine, inverse sine of 1/2 equals 30 degrees. That was 2 and 6 from the previous page. And here I'm going to get that again. So I know that the inverse sine of 12 over 24 equals 30. So I know 90 minus theta equals 30. That's a one-step equation. I could solve it to get theta is 60. And is that fewer steps? No, but that's where my brain went. And I like thinking in all of its forms. Okay, next problem. Last problem. Woohoo! Full page problem. All right, Peter. Peter cannot figure out what he has done wrong. What have you done wrong, Peter? He wrote an equation below to solve for the missing angle of a triangle, but his calculation gives him an error message every time that he tries to calculate the angle. Peter's work. I'm going to rewrite it because I'm pretty sure it's blurry on your screen. Cosine of the angle is supposed to be 8 over 2.34. Nita, his teammate, looks at his work and says, of course your calculator gives you an error. Your cosine ratio is impossible. What is Nita talking about? And how can she tell without seeing the triangle or checking on her calculator? Let's draw the triangle. I'm intrigued. I know it's the right triangle because I'm using cosine. SOHCAHTOA. Cosine is adjacent over hypotenuse. So I must have cosine of my angle equals adjacent over hypotenuse. Based on my drawing, opposite is there, adjacent here, and hypotenuse is here. I think I know what mistake Peter made. All right, so if I've got adjacent and hypotenuse, that means I'm saying the adjacent is 8 and the hypotenuse is 2.34. 8, 2.34. This doesn't make sense. This doesn't make sense. I think this doesn't make sense because it means the adjacent side of the triangle is longer than the hypotenuse, but a hypotenuse is defined as the longest side of a triangle. So we have a contradiction. In college, I learned, everybody, that contradiction can sometimes be written with this little lightning bolt arrow, which I like. All right, so my guess is that Peter switched the adjacent and the hypotenuse and just made a mistake. And my guess is that our textbook is including this problem because it's such a common error. I do see students making this mistake a lot, where they write their fractions for sine, cosine, or tangent upside down. For sine and cosine, that'll give you an error message, so you know that you have a mistake to check. But for tangent, it would still return a value. So just take care and try to work with the level of precision in your work. And if you make a mistake, go back, check. This might be the mistake you made. Anyway, I had fun. I hope you have a great day. And yeah, that's it. See you next time. Bye.